Hello and welcome to this presentation titled Masked and Classify, Multi-Instance Segmentation for Surgical Instruments. My name is Thomas Kurmann, and this research was conducted at the University of Bern in collaboration with Intuitive Surgical and the Bern University Hospital. In the last couple of years, we have seen an ever-increasing number of laparoscopic surgeries performed using minimally invasive surgical robots, with the most widespread system used being the Intuitive Surgical Da Vinci. While these systems promise to increase surgeon dexterity and reduce complications, they also allow for many assistive computer vision-based applications, given that the visual guidance of the system relies on the endoscopic video feed, such as seen here. This has led to numerous different applications including pose estimation, augmented reality, and tracking. A large amount of these applications rely on the correct identification of surgical instruments in the endoscopic feed. While this task has been tackled in the past mainly using semantic segmentation-based approaches, results so far have only been promising for cases where a simple binary segmentation or a part-based segmentation of the instrument is required. For cases where the corresponding instrument type class or instance is required, these methods have shown performance insufficient for practical purposes. A large limitation of semantic segmentation is that it does not provide instance-level information, which makes it difficult to disconcern objects. Extending a semantic segmentation-based method for instance segmentation is not as straightforward as, for instance, simply detecting regions. For one, instruments can be overlapping, leading to disjoint or occluded regions, such as seen here. In both cases, an assignment of pixels to an instance would not be possible. Furthermore, detection of the instrument type is only possible in many cases by distinguishing the clasper, as the shaft is shared among many instruments. This requires information from the clasper to be shared with any pixel in the shaft over large spatial distances, something which semantic segmentation methods typically struggle with. As we have seen before, semantic segmentation does not provide us with sufficiently detailed output to tackle the problem at hand. In order to provide instance-level information, we propose to use an instance segmentation method, where we assign every pixel P an instance number I and an instrument class C, where 00 is reserved for the background. This more detailed output is especially important for pose estimation methods, which rely on 3D CAD model registration. Many previous methods in the field of instance segmentation, such as the famous MaskR CNN, have made use of extracting bounding boxes around objects, and then performing subsequent segmentation and classification. For a particular use case, this is ill-suited, as surgical instruments typically have an elongated and rotated shape. In the example below, the ultrasound probe with the green bounding box would completely encompass the other two instruments, making it difficult for the method to choose the salient object. Furthermore, an object along the image diagonal would potentially cover the entire image. To overcome the aforementioned issues, we propose our mask and classify method. The main concept is that we first mask all object instances, and then classify them independently, using only pixels which belong to that object. We use an instance segmentation-based method, which does not rely on bounding boxes. The advantages of our methods are manifold. For one, our instruments can be of any size, shape, and rotation, as we do not rely on bounding boxes. Then, even with overlapping instruments, we can classify every instance independently of the others, as we first extract a pixel-wise mask before classifying it. Finally, our method naturally aggregates global information to achieve a coherent prediction for all pixels in an instance. This diagram below depicts the network architecture that our method uses. We use a shared encoder, in this case an efficient net, with two decoder heads, one for segmentation and one for instance extraction. We reuse the features from the segmentation head and classify them using a lightweight classifier to obtain our instrument classes. In our segmentation head, we predict a binary or part-space fine-grained pixel-wise prediction of the instrument mask. This is similar to what previous work has focused on. In our instance head, we predict two outputs. For every instance, we predict its centroid. And for every pixel in an instrument, we predict the offset vector from the pixel to the centroid. In this stage, we combine the two heads. First, we mask the offset using the segmentation mask, such that only pixels which actually belong to an instrument are retained. Then, using the offset vectors, we assign every pixel in the offset mask to its centroid. We do so by adding the offset vector to the pixel position and then finding its nearest centroid. This will give us n instance masks, where n is the number of centroids detected, as seen here. We then use these masks to mask the features coming from the segmentation head and individually classify every instance to its instrument type. All parts of the network can be optimized using a joint loss function, which is detailed in the paper. We are able to train the method in an end-to-end manner, but choose to train the classifier using the ground truth masks, as the initial outputs in early training epochs of the previous stages may lead to suboptimal results. Furthermore, we remove training examples where the clasper is not visible, as these examples are not classifiable, even for humans. We perform experiments on the 2017 IPCAI Endoscopic Vision Challenge, which consists of 8 training and 2 test sequences captured on an Intuitive Surgical Da Vinci Xi system. The dataset provides labels on a per pixel level for instrument class, parts, and instance. In total, 7 instrument type classes are present, including the background, as seen here. In our first set of experiments, we use a fourfold cross-validation according to Schwetz et al. We compare the previous methods using the mean intersection over union. The first 2 methods are semantic segmentation-based methods, which show similar performance for the parts segmentation. In the type segmentation, they show a strong decline in performance. ISINet is a mask RCNN-based approach, and also shows significantly lower performance than our proposed method. In this video, we see that the semantic segmentation cannot properly share global information across large spatial regions, which results in instruments obtaining multiple different classes, such as seen here. In our second set of experiments, we perform an ablation study to highlight the design choices that we took. This time we use test sequences 9 and 10, as they are less biased than the previous data split, which tests on the validation set. We compare 4 different methods. Ours using only a semantic segmentation-based method, ours using a single decoder head, sharing both instance and mask generation, ours using binary segmentation, and ours using parts segmentation. Evident is that the choice of network architecture, so the encoders and decoders, already increases the performance over previous methods. But combining instance extraction and mask segmentation into a single decoder does not increase performance over semantic segmentation. Finally, we see that binary segmentation leads to similar performance as the parts segmentation. This may be explainable that the network already learns implicit representation of the binary classification features, and as such, the parts-based guidance does not further increase the performance. Nevertheless, for practical purposes, we prefer the part-based mask. In these results, we see that the instruments are masked fairly well and that the class is detected correctly in most cases. Instances are properly separated, even in difficult cases, yet it sometimes fails when the clasper is not visible, which is to be expected, such as here. Up till now, we have not made use of any prior information from the robot. Yet our method can in a simple manner leverage kinematic information from the robot by using the instrument present as an additional input into the classification network. We do so by adding an additional fully connected layer to the network and concatenating the instrument present as a one hot encoded vector. This results in another leap in performance of nearly 20%. In the results, we see that while there is no significant change in the instance mask performance, the classification performance is less noisy, and even in cases where the clasper is hidden, it leads to correct prediction, such as here. To summarize, we have proposed a novel method for multi-instance segmentation based on a masked and classified approach. We have shown that it significantly outperforms all previous methods. In the future, we wish to extend the method to panoptic segmentation to also include uncountable objects and also include a temporal fusion to further increase the performance. I would like to thank you for your time and look forward to meeting you at IPCAI.